My name is Michał Kowalczykiewicz, and I have a presentation for you with this romantic title. But first, let's start with a bit of history. So in 1972, Prolog was created. It was the first logical and declarative language. A bit later, Datalog. I think it was in 1977. And Datalog was a subset of Prolog. And it was mainly made for declaration of databases. A bit later, Shapiro, it was in the 80s, Shapiro created the concurrent Prolog. And what is interesting about this is that still there is a, maybe not huge, but quite big community around these languages. For example, the newest version of Prolog, you want to guess, was released January this year. But what is not so good about this community is but the communities around these languages are mainly around universities. So none of these languages hit the mainstream or became popular. In comparison, there are the languages like the ones which you know, which are extremely popular, which are declarative, but not logical. But then in the late 20s, boom, LogicBlox. So the company called Predictix from Atlanta in Georgia, which merged with Infor a year ago, created LogicBlox. And LogicBlox is a smart database, and application platform for big data, for computation of big data for retailers. So it's solving problems like forecasting, replenishment, or demand management. But what is the most interesting for us during the next 25 minutes is the logical. So LogicBlox came with the logical, and LogiQL is an implementation of first-order logic. This is a superset of Datalog, and it's even more declarative than Prolog, because in Prolog you still need to have the correct order of the predicates, and in logical the order of predicates doesn't matter at all. And the grammar is quite small and quite neat, but I will show you how do we code in logical. So usually it takes a couple months to learn declarative languages, but for Scala developers, I think 5 minutes is enough. So we have just one concept, the predicate. To use a predicate, first we need to declare it. And declaration is like a signature of the function, signature of the class in Scala. So for example, here we create the entity predicate called item. So it's like a class in Scala. Yeah? Here we create the new predicate, which is a relational predicate. So this is like a relation in algebra. And we have also the functional predicates. So the functional predicates, when you see, I'm curious if you see this rounded, not rounded, but the square bracket. So thanks to this, we could say that there is a one-to-one relational mapping between the item and the description. And this export keyword is here. This export keyword is like a public in Scala. So thanks to this, in different places of code, we could reference these predicates. Or also we can populate them. But declaration is not all. We also need to have the definition. And definition is a way to describe how our predicates relates to the different predicates and how the different predicates relates to our predicate. And there are two kinds of definitions. So the first one is the constraint, and you see the arrow is from left to right. And you can read it like this. If I is item, then I should have a description, and I should have a from supplier. So these commas here are like ends. For ors, we have semicolons, and the underscore is like wildcard in Scala. And second thing is you need to have the rule, and the rule is the arrow from right to left. And we can read it like if we have two different items, and these two different items have the same from supplier, and these two different items have the same SKU, so it means that these two items are not unique. We have the keyword of alias all, and this is like the import in Scala. So we could put here the different predicates from different parts of the code. And we have the block, the block keyword, because we are grouping all of our predicates into the blocks. And on the runtime, we could turn or turn off some kinds of the blocks. And there is much more. We have the extensional predicates, we have the pulse predicates, and pulse predicates, these are the predicates which are disappearing after some transaction. So they are not true, or they are not false, they are just completely disappearing from our workspace. We have compiler pragmas, where we could disable some warnings or enable some errors. There is many more, and there is something what you like, because there is a way to declare a constant, so like a val in Scala, with the functional predicate, which is a zero arity, and that kind of predicate is called a scalar. Okay, so why do we use logical? We use logical because of big data, because when you use the predicate, it's easy to fulfill the concept of moving the computation to the data than the data to the computation, and logical perfectly fits as a model for optimization techniques like data flow graph or the incremental maintenance. And I will show you one small example. So for example, if you want to calculate the fun predicate, we could run this calculation on one core, this calculation on the second core, and the third one on the third core. Okay, so why the rendezvous? It was the intro, let's say, of my speech. And probably you are now guessing where is the Scala. Okay, so there is so Scala will be in, I think, 5 or 4 slides, but first have a look. Logical is great for us, but it's not perfect. For example, this is a real code from the forecasting application, which is doing the feature extraction, and this is a second code from the same application from a different file, and as you see here, there are a lot of similarities. Yes, you have in the head of the predicate of the rule. Sorry, we have the feature key, the same in the second file. Also, the body of the rule is pretty similar. The problem here is that, for example, in Scala, we have a lot of abstractions like classes, subclasses, or lambdas. But in logical, or almost all logical languages, we only have the predicate. So to show you more this problem, let's consider the example that you want to have the ABS fun predicate. Sorry, ABS fun predicate, which based on some fun predicates is giving us the absolute value. So for example, if the fun predicate gives us -5. Some goes or? Oh, okay. Okay. So what I was saying. So let's assume that, for example, the fun predicate gave us -5. We want to have that ABS fun will give us 5. And the problem is that if the fun predicate will change its arity, so for example, it would be like this. So we'll have also color and style. We'll need to rewrite the whole definition and the declaration for the ABS fun. So there is an extremely small reusability with inside logical. Maybe not totally off, but it's small. But it would be great if instead of writing again and again the new signature with only small, changes in the code, in the declaration and the definition, it would be great to have something like this. To have some abstraction that ABS fun will take some fun and will generate some code. And here comes the Scala. So we did in our company code generator. We started some time ago in Scala. So let's first create a model of the logical inside Scala. And to do it, we did it in the abstract syntax tree. So the first concept, the major one, is the predicate, and we have a class predicate which has a name, which has a key, which is a sequence of types, which has a value, which is a sequence of types also. And we have different kinds of predicates. So this is one you see these booleans like calculated, one-to-one, or pulse. We have these types, so we need to declare the types. So our types are primitive, numeric, int, float, boolean, probably something what you saw in the different languages. And we have this type of the entity predicate, which was on, I think, fourth slide. And the next thing is we need to have in the ABS tree, we have the terms, which are the leaves on the tree. So for binded variables, these are the terms. And for terms, we have the variable, we have the constant, the different one for int, for float, decimal, and so on. The situation is, but with predicates, we cannot build the rule, because in predicates, values are not bounded, variables are not bounded, so we need to have the bounded variables. And bounded variables are called the atoms. And as you see, atom takes a predicate, takes the sequence of terms, so something what is concrete, and the value space is also the sequence of terms or something what is concrete. And you have conjunction and disjunction. It is what you saw, so this commas, the ends, and disjunctions, the ors of the atoms. And with these atoms, we are constructing the clausure. So you saw on the first slide the constraint and the rule. And what will be good to know for the examples which will follow, rule is a headex. So this is a sequence of the variables, plus the head, which is the sequence of some formula, and the body, which is the formula. And we had this block in logical. So we composite all of these values inside the modular block case class, which has everything what we generate. Yeah? So we have pragmas, entities, clauses, and so on. And we have this, something called isGenerate, because we are sometimes switching on or off some code generation for some parts of the flow. Okay, so let's do first some extremely sample generation. It will be generation of the static code, so something what we do not generate. Because if it's static, we just code it in logical. So one by one. We want to generate the block with the name item declaration, which exports one declaration of the entity predicate and exports one declaration, export declaration of the functional predicate. So in Scala, it is extremely easy. We have one item entity, key predicate, and our generate method will return us the modular block, and it's like this. So the block name is static, it's item declaration. Entities is just one sequence of the item, and export price is also just one item in the sequence. But this is the static code generation. So let's go for the next example from the one of the, I think, fifth slide. So we had this problem with the ABS fan, and we wanted to have this. Yeah, everyone knows the concept. Okay, so let's create a function in Scala which takes a predicate, and we could assume just, I don't want to do any assertions here or some more code, but this predicate is functional of any RET, so it could be no values, it could be unary, or it could have even more values, and it's returning as a type of float. And we want to create, to generate a rule which consists of the headex, or it means the variables in the head. It consists of the head and the body. Okay, so let's start with the headex, and I don't know if it's visible. So in the headex we have these 4 variables, yeah? x0, x1, x2, and v. And they are let's say two problems which we need to solve. First one is we need to have some kind of the pool of all of the possible variables, because we cannot create, for example, for 3 variables or for 5 variables, because we don't know what is the RET of the predicate which is the fun. But we could assume that we won't have more than 20 variables in a rule, because truly speaking, I think if a rule has more than variables, it means that it needs to be refactored. And the second problem is we need to have some kind of a type map, which is providing us a binding between a type and the variable. So thanks to this, the x0 will be bind to the correct, in the head of the rule will be bind to the correct place in the signature, and the same will be bind to the correct place in the x0, in the fun. Okay. So to create the whirlpool, I think it's pretty straightforward. And we create the new method on the side called allocate, which is binding the types with the variables and putting it into the toMap. So our type map is like this. We are filling it with the keys, the key space of the fun predicate. And one thing is still missing. So we bind that. We have the predicates for x0, x1, and x2. And the missing thing is a variable for foo. We could add it statically. Another thing is, so now headx are all of the values. It's the value set of the type map. And it's a set, so just a simple map. Okay, so next thing is the head. So the head is this. So this is a ABS predicate, but it's not a predicate because we need to have the binded variables. We need to have the atoms. And we need to create a sequence of atoms. So it will be a sequence of only one element, only of this ABS fun. So let's again, on the side, create a function which will bind the variables to the predicate and will give us the atom. Okay, so it's a bind keys. And we could do it more generic, but it will give us the lambda, which takes the term, and give us, based on this lambda, will give us the atom, and this term will be in a value space. It's clear, guys? It's okay? Okay. Okay, so in our head is a sequence. We use this bind keys method which we created, and we need to put here the ABS fun, but we do not have it. We only have the fun, but ABS fun is the same as fun, but with different name. So we could just copy then they have fun function, and that's all. And we are feeding the lambda with which variable? We are feeding the lambda with variable foo, and we have the atom. So we have the head. Okay, so next thing is we need to have the body. And the body is a formula. And formula is here a sequence of conjunction, because we have the comma, yeah? So it's a conjunction of two atoms. So what is missing? The missing thing for us is the float ABS, because we do not have that predicate. And the idea is that in LogiQL, there are a lot of built-in functions. For example, for ABS, there is a function for float ABS, int ABS, decimal ABS. So maybe we could write a generic thing which will generate per type the correct ABS we want. So here, the ABS is a lambda, which takes as an input the type, and it's creating us a unary predicate. Is this ABS plus some type. Okay, guys, could I? Okay. And the body is like this. So, step by step. We need to have the variable. The variable which is missing is the x. Yeah. We want to have the atom for fun. And atom for fun, we could use the bind keys method, which we created before, and apply to this the x, yeah? X here, so this is the x here. Now we could create the predicate for ABS. So for this guy, for this guy. We are creating it here. But we want to have the atom, so we are just feeding the formula atom with this predicate, with the sequence for the key space and the sequence for the value space. And what we are returning, only the formula, which is the conjunction, because we have the ends here, of the sequence of fun atom and ABS atom, so of this and of this. So we have everything. We generated some, let's say, generic LogiQL code, and in the fact, I will show you the real example. So in LogicBlox, there is a concept of proto-services, and proto-services is a way to handle HTTP requests, like post, gets, puts, and so on. So I think how it works will be straightforward. So we have the message with the request. You have the request, you want to have the response, and in this response, we want to have all of the items which are in a database. So this is a code written LogiQL manually, which does that. And what is interesting is this. So these bolded predicates are only used here, but the declaration and the definition for all of them was auto-generated. So with alias all in another module called protobuf-gen, we have all of the definitions and declarations generated. And in fact, so we are able to generate some small pieces of logical. And in fact, some time ago, we started to generate whole applications. The process is called model Refinery, and how to read it. The idea is that we want to have the new LogicBlox application, and in the past, we'll just sit and write everything manually in LogiQL, but now we have three inputs. So the first one is a pool of static code, because for sure, all of the applications could share the same set of predicates which are valuable or true for everyone, like the predicates for calendar, for example. The second input is the client-specific libraries, because for sure, each application is let's say, unique. And it's unique, so we need to create some pieces of LogiQL manually. So we are not generating things which are, let's say, not reusable. If it's only for one client, we are writing it in LogiQL. Okay. And the third input is a data model. And in our case, the data model is a set of JSON files. And this set of JSON files models the model of the client or of the application. And with all of these inputs, some magic happens in the code generator, and we have the new app created. Yeah, and it's called the model Refinery. So in fact, we have the rendezvous. In our company, the combination between Scala and LogiQL, I think it's a perfect fit. And even we do not have rendezvous, we have the romance, let's say. And just one thing on the end, we are in Wrocław, and we started our adventure with LogicBlox 10 months ago, and with code generation and using Scala inside LogicBlox something like 7 or 6 months ago. And thank you, guys. Thank you.